Hi, I'm Jimmy, and I'm going to be talking about series today. When we deal with series, we have a function where each solution is added to its previous solution. For example, if we have the function n starting at 1 and going toward infinity, we add every solution to every previous solution. Thus, if we start at 1, we add 1 to 2 to 3 to 4 to 5, and go on until we go toward infinity. Now consider the function 1 over n. If we took the limit of 1 over n as n went to infinity, we can see that every term will get smaller and smaller until it approaches infinity. For example, as we can see, it starts with 1, and then we add 1/2 to that, then 1/3, and 1/4, and we continue and continue until we do 1 over infinity, which is essentially 0. So now the big question is, when we deal with series, is when will the term get small enough to the point where each additional term would have such a minuscule effect on the overall solution that it will make the series converge to a certain number? Well, we can see this by comparing the rates of change. Here we see a number of different functions that all grow at different rates. Organizing them from the slowest growing function to the fastest growing function, we have at the very top of the list ln x, then x to the p where p is less than 1, then x to the p where p is greater than 1, then x factorial, and finally x to the x, being the fastest growing function out of all of them. Now, the faster each function grows to infinity, the faster its reciprocal will approach 0. We have the same functions as before, but only now we have its reciprocal. As each function's reciprocal grows toward infinity, their solutions get smaller and smaller. But like before, some grow faster than others towards 0. Now the concept behind convergence versus divergence when comparing rates is testing how fast each function approaches 0. If the function grows slowly towards 0, every term's solution will be large enough that when they are added together, the series gets larger and larger, eventually growing toward infinity and thus diverging as seen with 1 over ln n. Now there's a fine line between divergence and convergence, and that's at the harmonic series, or 1 over n. The harmonic series will diverge, and every function that grows faster towards 0, like 1 over n to the n or 1 over n factorial, will converge. And every function that grows slower than 1 over n, like 1 over ln n, will diverge. Now if 1 over n is the boundary between divergence and convergence, where every function that grows slower than 1 over n diverges, and every function that grows faster than 1 over n converges, is there any way that we can multiply some slow-growing function to take 1 over n and push it over to the side that converges? For example, can we take the series of 1 over n times ln n? Will that push it over to convergence? We can test this with the improper integral test, where we find the integral of the function 1 over x ln x from 2 to infinity. It doesn't really matter where we start, since we're trying to find the behavior as it approaches infinity to see whether or not it diverges or converges. When we first solve the integral, we'll have to substitute b with infinity, since we can't take an integral from 2 to infinity. Then we'll use u substitution to substitute ln of x with u and then solve. When we have the solution to the integral of 1 over x ln of x as b goes to infinity, we'll have ln of b minus ln of 2. Since ln of 2 is a constant, it can be ignored, whereas ln of b as b goes to infinity will still be infinity, even though its growth will be very, very slow. Thus, the series 1 over n ln of n diverges. In summary, by comparing the rates of growth of functions and how quickly their reciprocals diminish to 0, we can determine the convergence or divergence of a series. By comparing a function to the rates of growth on this function line, we can say, well, hey, if this function, 1 over square root n, grows slower than 1 over n, then it must diverge. Or if a function 1 over n squared grows faster than 1 over n, then it must converge. Now, when we have convergence, there are a number of ways to find what that function converges to, but that's for another time. I'm Jimmy, and thanks for watching.